All right. So now there's a issue that we should address. We've seen how to compute the eigenvalues and eigenvectors, let's say for n by n matrix, and we've always been, without explicitly mentioning, we've always been assuming that the entries of our matrix are real numbers. Okay. Now, from here, we get the characteristic polynomial whose roots are the eigenvalues. Eigenvalues of A. And now the problem is, or not really necessarily a problem, but the point to make, or the point to notice, is that roots of A minus Ti, determinant of A minus Ti, are in general complex numbers. Okay. They are not necessarily real numbers, even for some very basic examples. Right, for example, let's say A is some perfectly real matrix like these. Then the characteristic polynomial is 3 minus t minus 2, 1 minus t. And you compute this explicitly. T minus negative 2, so plus 2. That's 3 minus 3t minus t plus t squared plus 2. So t squared minus 4t plus 5. And the quadratic formula tells you what the roots are. Okay. So t is equal to 2 minus 4 minus 4, so 4 plus minus b squared, so 16 minus 4ac, 4 times 5, that's 20. So 4 plus minus root of negative 4, and that's, and divide everything by 2. So that's 2 plus minus I, right? And this I here, if you've never seen this before, this I is the complex unit characterized by the property that I squared is minus 1. Okay, so this is evidently a complex number, or these two are evidently complex numbers. Okay, so we must allow, or we must be able to deal with the fact that eigenvalues can be complex numbers. And this is important also in the process of solving for eigenvectors, right? Because now when your eigenvalues are complex numbers, solving the linear system would be you will require that you manipulate complex numbers. So let's spend some time on the arithmetics of complex numbers. Of complex numbers. Okay, so first of all, a complex number takes this form. Z equals to A plus BI. I is the complex unit. A and B are real numbers. This is what a complex number looks like in general. And A is called the real part. B is called the imaginary part. Okay. And so it's basically just two things add together. And if you just use the rule I squared equals to -1, complex numbers add and multiply in the same way as real numbers. So for example, A plus BI plus C plus DI is the same, is just A plus C plus B plus DI. Now A plus BI times C plus DI is just, you multiply it as if these are numbers that you know already. So distributive law applies. That's AC plus ADI plus BCI plus BDI square. And I square is -1. So this is really AC minus BD plus AD plus BCI. Okay, very well. Now there is a important notion of the for a complex number. Complex conjugate. If Z is A plus BI with AB being real, the complex conjugate Z bar is defined to be A minus BI. Still a complex number. Okay. And you can easily check that the complex conjugate satisfies the following property. Z plus W, the conjugate of Z plus W is the conjugate of Z plus the conjugate of W. It's one property. The conjugate of ZW is the conjugate of Z times the conjugate of W. Okay. And if you add Z with its conjugate, you get A plus BI plus A minus BI. That's just 2A because the multiples of I, the two terms are cancelled. If you take Z minus Z bar, you are doing A plus BI minus A minus BI. This time the A's are cancelled. You get 2BI. And finally, if you take Z times Z bar, you get, that's A plus BI, A minus BI. So that's A squared minus the square of BI. Because I squared is -1, this is A squared plus B squared. Okay. Now here's an important definition coming from this equation, ZZ bar equals A squared plus B squared. The norm of a complex number z is the notation being z, well, it looks like double, no, not double, sorry, just single. Looks like the notation for absolute value. This is defined to be the square root of real part square plus imaginary part square. This is the same as z bar, or z bar z, if you like, or the square root of them. Okay, now what do we do? So these are the basic things we need about complex numbers. Now, we also need to be able to work with vectors whose entries are complex numbers, right? So now we call these guys complex vectors. They're not anything really that complicated. It's you just have entries now being complex numbers instead of real. Okay, that's certainly workable. And you can see that these guys form a vector space. And we have with component-wise addition and scalar multiplication, they form a vector space. Now this one is denoted by c to the n. Okay. Right. Okay, so now we need some further notions for complex vectors as follows. So if you have a vector x in the complex vector space, its conjugate vector x bar is defined to be the vector whose entries are just the conjugates of the entries of x. So certainly still a vector in Cn. Now we can also define the norm of x to be, first of all, it's a double, it's like that for the notation. And this time what we're doing is we're taking the matrix product of the transpose of the conjugate vector with x. This is now, as you can see, this is actually a real number. Okay. And more precisely, what this is, you can see that x bar transpose times x is just x bar 1 bar x1, x2 bar x2, xn bar xn, and this is the norm squares of the x's. Okay, certainly real and positive. Now we can certainly also consider when you have two vectors, x and y, being complex, can consider this quantity. How do I want this? I think x bar transpose y, but we're not gonna use it very much. Okay, so these are the basic things about complex numbers and complex vector spaces. In fact, in particular, Cn. Cn. Right. Now we should move on to see how this is supposed to impact our ability to study eigenvalues and eigenvectors. All right, so going back to the previous example, A is 3 minus 2, 1, 1. The eigenvalues are, as we found them already, 2 plus minus I. Okay, so now let's solve for the eigenspace. So for eigenvalue 2 plus I, we need to study AX equals to 2 plus I x, i.e. A minus 2 plus I times the identity matrix, x equal to 0. Now you write the augmented matrix as follows. 3 minus 2 plus I is 1 minus I, minus 2, 1 minus 2 plus I is minus 1 minus I. Okay, and then you have 0, 0 here. So, okay. Despite the entries are now complex numbers, the idea is the same. You proceed to turn this into reduced echelon form. Question is just, how to do this, right? We're gonna be clever about this. We will multiply the first row by 1 plus I. And 1 plus I times 1 minus I is 2. 1 plus I, 0, minus 2, minus 1 minus I, 0. And then you see that the two equations you have are actually the same equation, right? Because they differ by a minus 1. So you really just have 2x1 plus 1 plus I, x2 equal to 0. This means that x2, or I don't know, maybe x1 is negative 1 plus I on 2, x2, and x2 is still x2. So the vector x is now x1, x2, and that's negative 1 plus I on 2, x2, x2. So x2 times negative 1 plus I on 2, 1, like that. Okay. So these are the eigenvectors, and they span a one-dimensional subspace in C2, right? As you can see here. Now for lambda equal to 2 minus I, you have to solve the system AX equal to 2 minus IX. That is A minus 2 minus IX equal to 0. And you can once again write out the augmented matrix. 3 minus 2 is 1 plus I here, and the 1 minus 2, 1 minus 2 minus 1 minus no, that's a minus 1 plus I. Okay, like that. And well, we can try to multiply by 1 minus I to the first row. That gives me 1 plus I times 1 minus I, which is again 2 here, and 1 minus I minus 2 minus 1 plus I. And then you see again that these two rows give you the same equation because they differ by a factor of minus 1. So you just have 2x1 plus 1 minus I x2 equal to 0, which you can solve. X1 equal to negative 1 minus I on 2 x2. So x, the vector, is equal to minus negative 1 minus I on 2 x2, which is x2 times this vector. Again, we found the eigenvectors. I guess one point to make is that these eigenvectors are complex vectors. So you're basically, because of the fact that eigenvalues are possibly complex numbers, you are forced to consider also complex vectors. And yes, and things can get complicated when you have that. So let's see. Let's do one more example. So RA, again, let's consider the entries are all real. Okay. So the determinant of A minus T, I. And well, this is something that it's going to take a while to compute. Okay. Don't seem to have any better way to go forward, so we will expand it on the first column. So minus 2 minus T, 1 minus T, 1 minus 3, 4 minus T, minus 1, so it's a plus 1 minus T, 1, no, wrong. So this minus 2, 1 minus 9, 4 minus T, and plus a 1, minus 2, 1 minus T, minus 9, minus 3. Okay, like that. Now we expand. Minus 2 minus T, 1 minus T. Well, let's not kid ourselves. Let's go a little bit faster. T minus 1, T minus 4, minus negative 3, so plus 3. Plus, so that's 2, T minus 4, minus 9, minus negative 9, plus 9, plus what is this? 6. 6 minus 9 copies of 1 minus t. No. 6 minus negative 9, so that's a plus. Okay, yes. Now what do we do? Simplify. Minus 2 minus t remains t squared minus 5t plus 4 plus 3 plus 7 plus 2t minus 8 plus 9 plus 1 plus 6 plus 9 15 minus 9t. Okay, this looks complicated. Well, we saw there's nothing else we can do. We have to multiply. So factor out the minus 1, we get t plus 2 inside. So that's t cubed plus cube minus 5t squared plus 7t plus 2t squared minus 10t plus 14 overall minus plus so this is 16 minus 7t. Okay, so what is this? Overall negative t cubed minus 5t squared plus 2t squared minus 3t squared 7t minus 10t minus 3t plus 14 plus 16 minus 7t minus t cubed plus 3t squared plus 3t minus 14 plus 16 minus 7t. Okay, now we are more or less completed. So minus t cubed plus t squared minus 4t, right? 3 minus 7 is negative 4 plus 2. Okay, what are we supposed to do here? Let's see. There are certainly some ways to try to factor this. Can we? Are we just gonna? Let's see. Maybe we're making some mistakes here. Let's check. Oh, sorry, I copied it wrong. The t squared term should be 3t squared. Okay, and then you can see that t equals to 1 is a root. Right, if you set t equal to 1, it's minus 1 plus 3, that's 2. Minus 4, that's negative 2, then plus 2, that's 0. So you have a factor of t minus 1, and the other factor turns out to be that. Okay, so the eigenvalues are t equal to 1, and whatever this is, 2 plus minus square 4 minus 4, 4 times 2, that's 8. So square root of negative 4, that's 2i. So it's 1 plus minus I. Okay, and so for the real eigenvalue 1 here, we certainly know how to proceed. So we will just try to study the eigenspaces for the complex eigenvalues, just to give ourselves some examples. Again, you're supposed to solve the system ax equals to 1 plus ix, or a minus 1 plus I x equals to 0. And, well, we need to compute now. We need the augmented matrix. So that's minus 3 minus I, minus 1, 1, minus 2, 1 minus negative I. What is it? 1 minus 9 minus 3, 3 minus I, and 0 elsewhere. Okay, so we're gonna have to get rid of the first entry. So we're gonna have to turn the first row into well, so what am I saying? We try to turn the first column into, well, we have to turn these two entries into zeros. It seems the easiest if we just switch the first two, first with the third. Yeah, let's try that. So that becomes 1, 1, 3 minus I, minus 1 minus I, minus 3 minus I, minus 2 minus 9. Okay, and then we can proceed in a familiar fashion. That is R2 plus R1, R3 plus 3 times I, 3 plus I R1. Okay, yeah, let's do that. So R1 stays the same. R2 plus R1 will make this entry 0, 1 minus I here, minus I there. Minus 3 minus 1, minus 3 minus I, plus 3 plus I is 0 as expected. Then you get 3 plus I from here and negative 2, so 1 plus I. Now finally, this is 3 minus I times 3 plus I. So what is it? That's 9 plus 1. That's 10. 10 minus 9, that's a 1 here. Good. Okay, so these rows are clear. The first column is cleared. Now we have to use do something about the second row. Now the issue or the complication is that this is a 1 minus I. So there's a usual trick that you can do in dealing with complex numbers is you can multiply by its complex conjugate to get to a real number. So in this case, if I want to turn 1 minus I into a real number, I multiply by 1 plus I. That's what I'm doing. So that becomes a 2. And we multiply 1 plus I with minus I, you get 1 minus I. Let's see here, minus I squared, so plus 1, so 1 minus I indeed. And the third row is the same, 0, 1 plus I, 1, 0. And now we can proceed. in the usual fashion. So R1 minus half R2, that will get rid of the 1. R3 minus, what are we going to do? Well, we have to divide by 2, and we have to divide by 1 plus I. No, we have to multiply by 1 plus I. Divide by 2, and we have to multiply by 1 plus I, R2. Okay, now carry on. R2 remains the same, 0 to 1 minus I, 0. Well, I guess at some point we will divide R2 by 2, but we'll do that next. 1 here, 1 minus 1 is 0. So we have here 3 minus I minus a half of 1 minus I. Okay, we'll deal with that in a minute. R3 minus 1 plus I on 2 times R2. So that will be 0 here. And 1 minus, oops, what is this? 1 plus I on 2, 1 minus I. And 0. Okay, and now we should divide R2 by 2. And also deal with the computation that we haven't finished. So 0, 0, 1 plus I times 1 minus I, that is a 2. Divided by 2, that's a 1. 1 minus 1 is 0. So the last row becomes a 0 row now. Very good. So now we have 3 minus half, 2, 5. And I have I plus a half I. Like that. Okay. Well, let's see here. So I think we can now proceed to solve the equation. And what this is saying is that x1 plus 5 on 2 plus 3 on 2i, x3 is equal to 0. x2 plus 1 minus I on 2, x3 is equal to 0. So x, the vector, x1, x2, x3, is equal to, well, the negative of 5 plus 3i on 2, x3, the negative of 1 plus 1 minus I on 2, x3, and x3. So that's x3 times this gadget. Okay, so now we've succeeded in finding the eigenvectors. Very well. We can do this. It's a bit messy, but it's not harder than what we've done before. It's just that now it involves complex numbers, and you have to use arithmetics of the complex numbers to do it. Okay, now we have some general discussions to talk about. So we are going to primarily worry about matrices with entries real numbers. So matrix, let A be again n by a matrix with real entries. Okay. Now, suppose let's make the theorem here. Well, maybe make the whole thing a theorem. Suppose lambda is an eigenvalue, an eigenvalue of A, and X complex vector is an eigenvector of A with eigenvalue lambda. Okay, and then the theorem says that lambda bar, this complex number, is also an eigenvalue of A, and the vector x bar is an eigenvector of A with eigenvalue lambda bar. Okay, so proof. So what do we really want to prove? We want to prove that lambda bar is an eigenvalue and the x bar is the corresponding eigenvector. So what we want is ax bar equal to lambda bar x bar. Right, so this is what we want. That equation defines that equation is the required property for lambda bar and x bar to be what they are claimed to be. So what we know is that ax is lambda x. Now here's what we're gonna do. We can take complex conjugate on both sides of ax equal to lambda x. We're getting ax bar equal to lambda x bar. Right? Now, let's say x is equal to this column vector as usual. And let's say A has entries aij as usual. Then we're gonna understand this equation a little more. Okay, so if x is like that, then lambda x bar is, what is it? Lambda x1, lambda x2, down to lambda xn, O with the bar. But as we've seen already, taking complex conjugate has the property that lambda x1 bar is lambda bar x1 bar. Similarly for the other entries. So what this really is, it's lambda bar times x bar. Okay. So now we process the left-hand side. Ax, what is Ax? This is A, right? Aij has its entries, and you have x still what it is. So the entries of Ax are the following: A11x1, A12x2, A1nxn, A21x1, A22x2, a2n xn, a n1 x1, oops, plus a n2 x2, a n xn, like that. Okay, so this is ax. So ax bar is just this same thing, but bar everything. 1 x1 plus a1n xn bar, a2 x1 plus a2n xn bar, an1 x1 plus ann xn bar. Now you can split the bar according to the property that we discussed about complex conjugation. It's equal to, you take complex conjugate on the terms separately and then assemble them. Now, here's the point, here's the key point of this argument. The A's, Aij are real, so Aij bar, the complex conjugate, is equal to themselves. So all these things here are just all these Aij bars are just Aij. All right. Now, what does this mean? Now, if you reverse this operation, you see that what this is just A times x bar. Okay, so we start with the equation A bar of Ax equal to bar of lambda x. We figure out that bar of lambda x is lambda bar x bar. And we figure out bar of Ax is Ax bar. So Ax bar is lambda bar x bar, which is what we want. Okay, very good. Now, next theorem says the following. If you have n by n matrix, real matrix, n matrix with real entries, if A transpose is equal to A, i.e. A is symmetric, then eigenvalues A are all real. Okay, so first of all, you see what this theorem means. In general, eigenvalues can be complex numbers, but if you have a symmetric matrix, the eigenvalues are real according to the theorem, and then we don't have to worry about the issues that we talked about. Okay, so suppose you have an eigenvalue, lambda. Lambda is an eigenvalue of A with eigenvector x not equal to 0. Then Ax is equal to lambda x. All right. And for the moment, x is a complex vector, so we're gonna treat it like 1 for now. We're gonna consider the following expression: x bar transpose times ax. Okay. Okay. Now what do we do with it? X bar transpose times ax. Well, ax is lambda x, so this is just x bar transpose times lambda x. So it's lambda times x bar transpose x. Okay. Now on the other hand, for u and v, any vectors, we have u transpose v equal to v transpose u, right? All you have to do is just look at the definition of this matrix multiplication. So in particular, we can write x bar transpose ax as ax transpose x bar. And this can now be processed slightly differently. The transpose of ax is x transpose a transpose. Now you have an x bar here. Now a transpose is a, right? So by assumption, a transpose is a, so that's just that. Now you have x bar, so x transpose a x bar. Now what is ax bar? According to the previous theorem, ax bar is lambda bar x bar. So this is just lambda bar x transpose x bar. So now what do we know? On the one hand, we have x transpose x bar transpose ax equal to lambda times x transpose x bar transpose x. On the other hand, it is equal to lambda bar x transpose x bar. So lambda x, not that. So lambda x bar transpose x is equal to lambda bar x transpose x bar. Now, x transpose bar, x bar transpose x and x transpose x bar are actually equal. They are just x bar x1 bar x1, x2 bar x2, xn bar xn. Okay, and this is not 0 because x is assumed not 0. So that means you can cancel them from this equality, which implies the lambda is equal to lambda bar. Right, you have a potentially complex number lambda equaling its own complex conjugate. That means lambda is real. And that's the proof of this theorem. Okay, so what this theorem is saying is, like I just mentioned earlier, although in general, even with real entries, a matrix has complex eigenvalues, but if the matrix is real and symmetric, the eigenvalues are guaranteed to be real numbers. So the process of solving for eigenvalues and eigenvectors do not involve arithmetics of complex numbers, which therefore is slightly easier, even though it doesn't really matter that much. Okay, so that's this lecture.